Hi, this is my another project that I have worked on a couple of hours for a stepper motor. So it's a bipolar stepper motor. As you can see, it has 4 wires. So these are the 4 wires, and 2 extra wire, which is the center tap of both the coils. So bipolar stepper motor has 2 coils which are placed 90-degree apart, and so these are the 4 wires of both the coil, the 2 ends, and the center is brought out, which I'm not using, and it's a pig board, general purpose board, so I'm using the 6 signal wires, 4 for PWM and 2 for enable, and driving is through the LM298. So these 2 boards are like what I purchased, locally available in India. Pretty low cost, and the code that I have written is to drive the stepper motor in microstepping mode, so what is also called the sine-cosine drive. So what is a sine-cosine drive is basically when you have a 2 winding stepper motor or a bipolar stepper motor. It's also a electrically it's a 2-phase motor. So if the permanent magnet in the rotor, so it can be assumed as a 2-phase kind of permanent magnet kind of motor. And so to drive it for any AC motor, we need a revolving magnetic field, and in this case it is produced by a signal which is sinusoidal and another signal which is 90-degree phase shifted, and becomes the cosine. So this drive is also called the sine-cosine drive. And so let's see how does it work. So I'll just switch on the power supply, so you can hear the hum probably. So you can see the motor is running. So this motor I got it from a junk Xerox machine. It's a very old, I think some 1980 kind of Xerox machine, and the magnet was pretty much safe sitting inside, the motor. So I just took it out, and so as you can see, the motor does not make any step kind of movement. The rotation of the motor is pretty much stable, so it's very smooth rotation, and that is one way to verify if it is a sine-cosine drive. And you cannot see any steps, so that's another way to figure out. So you can see the rotation is very smooth. And another way to check is to measure the current waveform of each of the phases. So these are the 4 wires which again goes out from here. So these are the 2 inputs. These are 2 inputs, and for one phase and another phase, so 4 wires. So I've connected the current probe to one of the wire. Let's check the signal. So you can see the signal is it's not exactly sinusoidal, but it's also not very bad. So you can't say it's a square or a typical stepper motor steps. So it's very much continuous waveform. Now the problem is I don't have 2 current probes so that I can probe the signal on both the phases, but I just have one. So you have to assume that the other one is 90-degree phase shifted. So 90-degree phase shifted means if this is the sine, if it starts from here, let's say 0, the other one will start where the sine is at the minimum, where the sine is the maximum point. I'm sorry. So sine is at the maximum point, and there the cosine drive will start. So 2 90-degree phase shifted when given. So 2 90-degree phase shifted signal given to a winding, given to 2 windings which are shifted in phase, shifted in space by 90-degree, that will generate a revolving magnetic field. So to check the torque, how much torque this motor generates, if I put a finger, like I can stop the motor. Now that's well known for stepper motor, that as you increase the steps in stepper motor, the faster you step through the stepper motor, the torque of the stepper motor reduces. And unless you use a very sophisticated closed loop current control which maintains the current constant, the torque of the stepper motor, which in this case I am not using any current control, the torque of the stepper motor will reduce, so it is significantly lesser. So you can see I can actually stop. Now one way to increase the torque of the stepper motor is to increase the voltage, so that will make sure that a higher current is pumped through the windings. And let me try to stop it. Yeah, it becomes little difficult than what was earlier. And check the current waveform. So current has even become higher in amplitude, and it has become more of kind of sinusoidal. So that's one more. And if you can actually measure the frequency of this sine wave, and if you know the number of poles of the stepper motor, which in most cases we won't know, then when manufacturer, they don't specify how many number of poles, because again the number of poles, they multiply it by making kind of teeth on the rotor, so that multiplies the number of poles. So it's kind of very difficult, but whatever it is, it's a sine-cosine drive, or a multi-stepping stepper motor drive running very smoothly. And so the overall idea of this project is that by using a peak controller, which is a peak 18, and by using LM298, and by writing a very small piece of software, and by using two PWMs, that is CCP1 and CCP2, and using some general purpose IO pins, you can drive a stepper motor. And if we give sufficient voltage to the stepper motor, it will also generate sufficient torque. And so if somebody is planning to make a robotic drive out of the stepper motor, they can easily connect a wheel, and then so it will run pretty smoothly. Now another factor which is also well known of stepper motor is that their efficiency is very low, and that's because we basically run them in open loop, not like a BLDC motor where we maintain a relation between the commutation of the phase and the position of the rotor. So the position of this rotor in this case is not known, so we just run it and make sure that the rotor is actually following the steps, or in this case the revolving magnetic field. And so another look, so this is the normal running. So if I put a load, if I stop the rotor, the current basically rises from 140 milliamps to about 200 milliamps or 190 milliamps. So I think that's all I had for today. Thank you.